All right. Disclaimer on this presentation. Everything in here is essentially float design according to me. It is not necessarily, these opinions are my opinions and not necessarily those of anybody else. So that standard disclaimer. Having watched a number of parades, I think that floats can be broken down into three different categories: story floats, flower floats, and just plain old commercials, which I wish a tournament would figure out a way to get rid of. A story float has a central joke or a theme. It needs to be understood for you to really understand what the float is, and it has some sort of tie to the parade theme. The flower floats, they could basically go in any parade. They're just a whole bunch of flowers thrown in place and something pretty, but these are what typically win the sweepstakes trophy. And then we'll commercials. So
Jane Goodall, meaning
a few examples of floats. So here you got Dinosaur. Very simple, one big central character. It's got the wings on its back. Doesn't take much to get the idea. Another float that we did. Pigs, if pigs could fly. You don't have to really stare at this float for any length of time to get an idea of what it is. You don't even need to read what the title is. In this parade. 3, 2, 1 dig. This was one where we missed it, in my opinion. When you listen to the commentary from the different commentators, they all kind of are trying to figure out what the story really is, and they all have different stories. And so people didn't understand this float when it first came around the corner. All the story really was we want an excuse to have excavators dance and make something with big animation.
A volcanic eruption there.
So here we've got our floral floats. I mean, I have no idea what the parade theme was this year. But it's a pretty float, and Dole won a trophy. I think probably was the sweepstakes trophy for this float. A lot of drives, but then the flowers make pop. Here's another one. A lot of little details, a lot of intricate decoration in the drive. But it was a good float. Sierra Madre, they just put in a huge amount of flowers. And so, I mean, it's a pretty float, but you wouldn't necessarily know what the parade theme was for this. Wow. Now let's look at a few of the plain old commercials.
You are the controller.
This young lady is just,
I mean, I don't even give these ones much time, but they're just throwing off showing something about a product that they're trying to sell. I mean, I don't know if you remember, farmers had a whole ad campaign around this, whatever it is. So, different ones. Now, I'm going to concentrate on story floats because that's what we typically build. Important, clear, concise story. You need the audience to be able to understand what the story is quickly. If it's got inside jokes, complex storylines, cultural references, all those can get us into trouble. I mean, we did self-built float. Nobody understood what it was. It was an inside joke, and it just didn't go over well. Also, be careful about adding details. Sometimes adding extra little details around the base to fill things up just confuse the audience and lose the story. A few other things. No matter how, I'm an engineer, I love animation, but the parade is a floral parade. Animation is just a small little piece of our score. And you got to remember, the average viewer just wants to see things moving. They don't really care how complicated the animation is. But the animation can be very useful for helping to tell the story. But the real concern is if animation is required to tell the story. If something fails, if something doesn't go right, then you can actually lose the entire float based off of that. I mean, here's some animation trophy winners. This is one of ours, another one of ours. A lot of animation, a lot of spinning, big motions. Easy to see the motion. This one, there was only really the one piece of animation, and this one was actually all manually controlled animation. But it won the animation trophy because it was big and it really moved. Another animation trophy winner, Trader Joe's. A lot of spinning and moving things. All relatively simple mechanisms, nothing super complicated, but it was a lot of motion. And we have one more, Farmers Insurance, should be coming on in a moment. And this one was just another bunch of spinning animation, simple things. But that's what often wins the animation trophy. The judges don't appreciate what goes into the mechanism. So be careful about spending a lot of time designing something that people aren't going to appreciate. When thinking about what you're going to animate, do you have a logical recycle? Is the motion going to show? Is it big enough? Is it moving fast enough? We did one with a trolley and it rocked from side to side, but because the trolley was so huge, we ran it at such a slow speed that people didn't really even notice it moving. And so all that effort to get that thing to move really didn't come across. The other thing you got to be careful about is linear motion. Anything that's going in the same direction as the travel of the float doesn't necessarily show, because people are just seeing the float moving towards you and not necessarily that the motion is also moving towards you. Think more of stuff going side to side really helps. And then just, is a mechanism worth the effort?
Bending the rules is what Cal Poly often does.
So this is one of my early ones at Cal Poly.
From those innovative students of Pomona and San Luis Obispo.
One of the problems we had
Cal Poly University
on this one
campuses,
was
a strange game of basketball here.
There was a mechanism inside of this mouse that was supposed to make it lean forward and tilt forward and back so that it could actually do the slam dunk. Well, that mechanism failed and we weren't able to fix it. And so a lot of the whole sequence got lost because of the loss of one piece of animation.
Jungle critters banded
and
together,
then the sequence wasn't programmed quite right.
And
so it never really worked.
A system that might actually work.
I mean, you can see things are out of sync, and it's just not working, and there was no real logical recycle on this.
Holding the basketball, and
however, or Tea Time 2000, one of the little jokes that we put in was right here. There's a gopher. And so as this golfer went to strike the golf ball, the gopher would actually drop down inside of the float, pulling the golf ball down inside. And so the golfer would miss his swing each time. And so it gave us a logical way to reset the animation sequence and go from one cycle to the next cycle. A few other thoughts about animation. Collision zones are bad. If you can avoid them, avoid them. Having an engineered near miss is just as impressive as a collision zone. We had on Dinosaur a couple of wobbling eggs, and we had set those up in such a way that they were a random pattern, and every once in a while the eggs would get within about a half an inch or even closer to each other. And one of the judges spent a bunch of time just staring at those eggs wobbling, looking for them to hit. It wasn't a collision zone. It was a just miss, and it still got the judges' attention. And I'm going to say 99% of the parade viewers are impressed with just spinning stuff.
Now, what could be more conspicuous than two giraffes in love?
Now, here's an example of a
the name of the Flintridge
mechanisms that
Michael
were done
Johnson,
years
the engineer
ago.
for this float, has been engineering and animating Roseberry floats.
I have to admit, this was one of the most impressive floats I've ever seen.
He has had to
the way these two necks intertwined and moved was just amazing, and it's what actually drew me to come work with the locking out of float.
So that it doesn't
However, this float did not win a trophy.
Very intricate.
And while I wasn't involved in it, I want to believe that the reason why this one did win a trophy is because so much time and effort was spent on on building those necks that they weren't able to spend time on the rest of the neck of the float.
Open to the entire community. So this is what is called a self-built float. Renee Haas Johnson, the designer, floral director, Judy
Then
Mitz,
we also have
beautiful work.
This one, which nobody just ended up getting. A lot of collision zones.
All smiles down here for this one. The Lackawanna Flintridge Tournament of Roses Association bringing out the deep and hit some crucial water pipes, much to the surprise of that palm fiber and pampas grass covered gopher.
Really
all that means the crane at the rear has no place to put the pallet of azaleas. Let's call them the Three Stooges of.
So just think about that whenever you're doing your mechanisms. A few heights that I always say for us, 16 foot 6 inches is the float manual height requirement. Anything above that needs a variance. 23 foot is essentially the maximum height we can use underneath the bridge for decorating. So in case we want to test animation under the bridge, or if it's a rainy New Year's Eve, we can do our judging under the bridge. 23 feet is about the maximum you can go. After that, you might as well build as tall as you really want to go. Other things that I've always felt were things that we try for, take as much off the float as you possibly can. A few exceptions, you don't want to be bleeding under the bridge. So if it's a rotary mechanism, we've done those with quick disconnects, and that has worked well. But yeah, be careful if you have to rebleed. Advantages, easier to build, easier to decorate, less scaffolding. But we also make sure you keep enough time in the sequence to get everything put back together. Just an example of on Dinosaur, some of the stuff that came off of the float. I mean, we even took the volcano on the back of the float completely off, and that saved a lot of time scaffolding and gave a bunch more the ability to get a bunch more decorators on the float decorating that large piece before we dropped it back on. This one was more aimed just at the Cal Poly people. Their ground clearance have been getting a little bit high at this point in time, but 8 inches is what the float manual says. We typically go for more of a 12 inches. Some of you may have heard what we used to call the 7-degree rule. And that is if you draw a line starting at where the tire hits the ground, going forward at a 7-degree angle, you need to keep everything out of that. And that's what we had found was necessary to get out the driveway if we don't put the wood blocks in the driveway. And then you also have that same 7-degree on the back end. With the wood blocks, we were able to find that you don't have to do that. A 12-inch ground clearance seems to work okay for us. One of the things we often forget about when we're designing the floats is how are we going to decorate everything and get people in. And so think about that as you're doing the build. On If Pigs Could Fly, the entire base was all screened and therefore couldn't be walked on. So we actually built in hard points that we then were able to put 2-inch box and then just put boards across, and that gave us the ability to returned our ability to walk on the top deck because we had enough scaffolding up there. Now, it was fun getting it off at the end, but we were able to find ways to do it. The other thing is, remember that your picks go straight through if you've got big structures in the middle, well, you can't necessarily run a pig through. So how are you going to get decorators into those locations? So for Dinosaur, we realized that there was whole sections of the float that couldn't be decorated off of picks and couldn't be reached from the deck. So we ended up coming up with these little scaffolding pieces that just allowed us to drop down so we could decorate the sides of the float and get our decorators into those right locations. But it's better to think about that before Deco Week so you're not making things at the last minute. But despite everything I just said, build what the float that you want to build. I've had the chance to build a lot of complicated mechanisms, and they've been fun, and I've enjoyed it. So I'm not saying don't do it. Just be careful that the rest of the float doesn't suffer. I mean, a complicated mechanism is going to cost you time, money, and physical space to do things. Sometimes we've had to give up certain. Think about whether or not the trade on the space that a mechanism is going to take underneath the float is worth the change in the float height or other details of the float. It might not be worth it. So mechanism design process. This is essentially what the process that I used to take. We have our concept, initial scale drawings, the rendering, and then going in and determining what to animate. As we're determining what to animate, we also need to think about the deco materials and come up with a rough weight of of the mechanism. Look at how much room do we have for doing that mechanism. And when you're thinking about that, don't forget about room to get the transducers in for the feedback. Sketch up the mechanism, do some calculations. I always like to model my mechanisms, look at what we're going to have to buy in order to make it. Depending on the mechanism, detail analysis. For some of the floats, we used to have a deal with Siemens where they gave us a copy of their CAD software and their analysis software. And so I was able to use the full FEA software to do analysis on it. But that was very time consuming. But some of the mechanisms required that. Cut list, build the mechanism, some testing. I like to have the mechanism done before we start shaping the character. But that's not always possible. So sometimes we're having to retrofit the mechanisms into the characters, which is always fun to do. Put it on the float, bleed. Make sure you leave yourself time for testing and for the computer guys to get in there and calibrate and program it. I also highly recommend on like the 29th or 30th, getting in there and actually getting some animation checks before, so you've got a little bit of time before final judging. Stow mechanisms. I've always say you should avoid them if at all possible. The audience doesn't get to see the work involved. Now, if you can design the stow mechanism to also be an animated channel, then people get to appreciate it. But with that said, it's not always possible to avoid this stow mechanisms. For If Pigs Could Fly, there were 3 dedicated stow mechanisms for that float.
Well, here's the winner of the Bob Hope Humor Award.
So
most comical and amusing.
It took me a moment to remember what the 3 mechanisms were.
The most impossible of all
but in order to get the height that this float really needed, we had to stow the main rotor. We actually had to stow this pig here because of the balloons on his back. And the third one wasn't obvious to me when I was thinking back on it, but it was the landing gear here underneath the gyrocopter, because the wheels actually would crush into the top deck if they didn't get stowed. So just things to think about. as far as your stow mechanisms, keep the operation simple. One of the things is you should have the ability to stow the float with no power. So no computer, no main hydraulic pumps. How are you going to get this thing back down into the envelope? And it's not just into the height requirement, but also into the width requirement. So if you're going out of width, think about that. In my personal feeling, the preference is gravity is always best. If you can design something so you just open a valve and it drops, that is the best. Another option is if the piece that's needing to get stowed is light enough, it could literally just be an operator that mechanically moves it. On one of the Cal Poly floats, we had a large barn, and on the top of the barn was just a little cupola that had a weather vane on top of it that pushed us over the height limit. But there were operators in the barn, and so our stow mechanism was just a big lever, and when it came time to stow it, somebody just grabbed the lever, pulled it sideways, and the thing stowed. There was no question about whether or not it moved. There was no, it was just plain simple. If gravity doesn't work, sometimes you'll need a hydraulic accumulator. A lot of our stows, I call are a bistable design. They go over center as they come up, and so then they sit in a vertical configuration, and then once you get them past that center point, they go down on their own, but they need just a little bit of help to get started. And that's where the hydraulic accumulator can often come in. And if you've got a really insane stow, you might have to put on an extra electric pump, which I don't think we've ever done, but it's just something to keep in mind. We normally use accumulator stows. On the float, we have a couple of accumulators, one that's typically set up as a stow accumulator. It's got a check valve that's used to charge it, a ball valve used to isolate it. One thing, as you're plumbing, make sure that you don't hook up that accumulator to any rotary animation. You'll use up all of your accumulator pressure before you even realize it, and then you won't be able to stow the mechanism. So, try and design everything and plumb everything initially so that requires the least amount of activity by the operators inside. The only time you're using these type of stows is something has already gone wrong, and depending on when it goes wrong, the operator cannot be thinking straight, and isn't necessarily in the right frame of mind to go, oh, I need to do this, then I need to do that, then I need to do this. And so it can get complicated. On our float Dinosaur, or that one unfortunately required a complicated stow mechanism and stow sequence. And so the night before T2, Jimmy and I were out at the float site for hours with him inside the float and me outside, running through the stow sequence over and over and over again until he could do it blind, because he was doing it blind. And even then, when we got into the parade, as we got to the tower to go underneath the bridge, we hear them yell at us, "Hi!" And so at that point, Jimmy just opened up one of the main valves and drove the nose of the dragon a little bit into the top deck, just to make sure we got down so we'd make it under the parade, with the risk of damaging some of the float. So not the best solution. Now, one thing is the computer does have the ability to do complex stow sequences if you've got the time to program them, but I'm still not going to recommend that if you've got a choice. So this is essentially the circuit that we've got set up from a hydraulic standpoint to do our stows. So we've got our this little U shape is a hydraulic reservoir. This is a pump. So flow comes from the pump. We have a pressure relief valve just in case something goes wrong and we get too much pressure. We filter it, and then we hit a series of check valves. So we got one check valve that comes up here to the accumulator to charge the accumulator. This is a manual ball valve that then gets shut off. We also have another flow path through another check valve. So if the hydraulic motor, or if the engine's running and we've got fluid coming out of the pump, our standard way, fluid comes through here, runs through the valve, and we're able to stow everything. If something goes wrong, the pump isn't running anymore, we can open this valve and you still have some hydraulic fluid in order to do your stows. Now, when you're doing your stow mechanisms, sometimes with where you need to get the pivots, things will get crushed. And I know a lot of the builders, the professionals, just accept that they're going to have crushable panels, and that's just built into their mechanisms. We try to avoid that. So here was the stow mechanism inside if pigs could fly. So with where the bearing needed to be, we had to get this whole section of the float out of the way. So we set up a 4-bar mechanism inside to just move this out of the way and allow us to stow. And it was all one control. So it wasn't like the operator had to stow the first item, then the second item. It was one control. Few other things. I like manual valves for stowing. That's the easiest way to guarantee you can stow it in case of a loss of computer. The other option is you can push the little buttons on the side of the valve banks, but then you have to have the valves close enough to the operator, and those can be a pain to do, especially if you're in the float, a little bit sleep deprived, and low light, depending on the location. For things that stow just based off of gravity, consider, and we've been doing this, what we just call a lock valve. So you drive it into the up position, and then you turn a valve to lock it in place so the fluid's not coming out. And so then you're not having to keep pressure on it. For one of the floats, we had a family getaway. We had a large canopy in the back. And that morning was a horrible morning. We discovered the pressure compensator on the pump wasn't set high enough to get the float, the stow mechanism up with all the decorated weight. We had issues getting the drive engine started. We were within seconds of getting towed when we finally got the engine started. But what we also found was that the canopy decided it wanted to keep coming down on us. So I ended up taking a rope off of one of the chocks that we were carrying in the float and tying the valve into the up position so that would stay up for the entire parade. Where if we had a lock valve, that would have saved that problem. Now, one thing we put in a few years ago are load holding valves. I'm not a super fan of them just because from an animation standpoint, they can cause jerky animation and you got to get those adjusted right. So something I would recommend, now Randy might have a different opinion on this, but when you replace the main valve stacks, I would consider going away from those, from the locking, the load holding valves and look at a different thing. One other comment is, despite even having locking valves, if you've got decorators working under something, you may also want to consider a physical hard stop to really make sure that decorators don't get crushed. Okay, so Also, when you're thinking about what to animate, you got to think about how are you going to hide the joints. Something that's animated but leaves a bad joint can often look worse than if it wasn't animated at all. One of the simplest solutions is concentric rings. So you can, here for Scissored Wizard, there were just 2 circular rings right at his shoulder, and that hid the joint. Here on Rainforest Fiesta, we had these 2 concentric rings for the neck. Now, the one thing I didn't like about this one is you can see how the paint pattern goes across the joint. And so as the head turned, this pattern broke as it went from one side to the other. It ended up wasn't too bad because of the deco material, but if you can avoid patterns going across the joint, it's better. This personally is my favorite way, and that is just finding a logical break line and then potentially even emphasizing where the break line is. So this is off of, I can't even, the Great Haldini. And so there's a seam line right here at the shirt collar. And so the neck goes into the shirt. And so it was just a natural point. The collar actually hides the joint. And so by putting more detail in around the joint, it actually made the joint less visible. Another option that you may have heard floating around is floating rings. So this section here is all done out of neoprene and bungee cords. So you've got steel rings that are supported in place using bungee cords. So it's kind of like the shaping of the rest of it, except instead of the long runs being steel and welded together, they're bungee cords so it can all float. The really nice thing about this type of design is there is no single pivot point, and it's all makes very natural, graceful movements. But it's an art to set up. And if you guys are going to go with something like that, talk to somebody who's done these before you go down it. There may be some hints that can be done. It also limits the deco materials that can be used. However, we did have success putting patches of carnations into the neoprene. You just have to be careful, and the decorators are doing it have to be extremely careful that they don't cut any of the bungee cords. So here's an example of floating rings in neoprene. So this whole dragon neck from here all the way up to here is all done with bungee cords and floating rings. And so it gave a very natural look to the motion. However, it takes time. So the alligator tail and bending the rules that we saw earlier, that was my first one I ever did. That one took me around 2 days just to do the neoprene. Another Cal Poly float, catch of the day. That one was a day. Now keep in mind, this was a Cal Poly day, which are longer than a La Cañada days. On Just Imagine, that one we just looked, that neck took around 2 days just to get the bungee cords and neoprene set up. And then on Cactus Practice, there were 3 of them. It took in the range of 4 to 6 hours a piece. So that was around 2 days just spent doing neoprene. This was a slightly different thing that we tried on one float, and I call it rigid floating ring. So you can see there's a ring section, then an inverted ring section, another ring section, an inverted ring section, another ring section, and then there was a section on the bottom. And if you look over here, there's a set of bearings at the bottom, and then steel structure that came up and held each of those ring pieces. And then we used bungee cords back to the main structure to pull it back and forth. And so that allowed this to sway from side to side and give us a natural motion. The problem, we were kind of forced into this one because I didn't think about how we were going to hide this joint. The main joint to make that robot sway back to was right here at the bottom. And so if we had just shaped a rigid structure, as it went side to side, it would have dug into the top deck really bad. And so we had to come up with another solution. And then what made it even more complicated is we couldn't go with a standard floating ring structure, because this portion of the tube right in here was all telescoping to get the character under height. So it forced us into this other solution that ended up worked really well, but it took a long time to set that up and get it working right. And also, it was not exactly easy for the decorators to get in here and decorate all the surfaces, but it worked. Another option that works really well if you've got the space for it is disappearing panels. I really like this one. So this was a scissored wizard. And so just everything had room to slide inside of the adjacent structure.
Here's another one of the self-built floats.
So when you watch
from which,
it,
a special place emanates, and it won the Fantasy Award for Best Display of Fantasy and Imagination. The La Cañada Flintridge Tournament of Roses Association. This was
so you can see all the panels
named
are just disappearing into another location.
It's called Scissored
Same
Wizard,
with the tail.
demonstrating how a little magic can
you just got to make sure you give the decorators
she
time
is a high school student from
to
Walnut
decorate
Creek,
all the
California,
surfaces.
Emily is, who won the
because there's a lot of hidden surfaces in that type of thing. So, you need to be able to move the float into all the different locations that it possibly will get during the deco, or every place it'll go during animation, it needs to get during decorations. Now, this, I think, is Randy's favorite way of hiding a joint, and that is hide it with a bush. Sometimes there's you just run out of other options, and just let deco hide it for you. So you can see right here, we've got the seam line. Because it was a side to side, you got a big gap on here. We couldn't do the concentric rings. None of the other techniques really worked, but it was right on the top deck. So we just put a whole bunch of floral right in front of it, and it worked. And actually, right here, you can see another horrible joint, but deco saved us on that one. All right, so let's get into some different ways of building mechanisms. Sliders and tracks. I personally don't like sliders and tracks if I can avoid them. Friction is the enemy. The cheapest way of getting around that is just lots and lots of grease, but it can often wear out over from the time you can't get into the mechanism anymore to grease it till the end of the parade. If I have a choice, I always prefer to go with a roller, or there's some engineered plastics out there that are actually very low friction. Now, if you have a single rail, you got to figure out how to keep things stable on it. The part may want to turn. Multiple rails, like shown here, these two sliders are more stable, but you got to make sure you figure out how to keep those at the same distance. For that, I would definitely suggest some sort of a tool as you're building it, so you can use one tool that goes across them at these two locations, and then go to another pair of locations and put it on, and just double check that or else these will bind. So here's a slider with grease, and you can see the jerk in it. Now, luckily for what it was, it wasn't too bad. I think we re-greased this after it. But this is a mechanism we've used a few times. So you got the cylinder here. There's a 4-inch throw cylinder, but we're getting I think with the lever arm we got a 2-to-1 multiplication. But one of the things you got to look at is, first off, this mechanism is pulling on the side, so it's wanting to make this twist, which will add to the friction in here. Also, this arm is coming off at an angle. So instead of just pulling this straight up and down, it's pulling it against this beam here, which is increasing the amount of friction, which is leading to that jerkiness. So adding a lot of grease right in here is the solution, or figuring out a way to do it with rollers or something else would have made these better. Same float. This was a large track that we wanted to do. So we used 2 circular tracks, and then we used these wheels to roll up and down on it. And in order to compensate for the 2 tubes not being perfectly at the same distance, it's hard to see, but there's a set of big compression springs right here. And so we actually preloaded this side against this side to compensate for these guys not being perfectly parallel. Now we got them pretty close to parallel, but they weren't perfect, and so that compensated. I used a total of 6 wheels, so we had 4 on this side and only 2 on this side, so that we also wouldn't cause a situation where we were bind by having too many points of contact. Now this mechanism got a little bit complicated, and right down here you'll see a cylinder, and this cylinder is actually what drove the mechanism up and down. So this horizontal cylinder drove a sprocket that then drove these other sprockets and gave us a 3-to-1 distance multiplication. So we got 3 times the distance that we got out of the cylinder out of the chain, which allowed us to drive the bunny rabbit out of the hat in under 2 seconds. So we were traveling 7 feet in under 2 seconds. And during our testing, I actually stood on this, and when Randy dropped the cylinder at full speed, I could swear that I felt air between my feet and this platform, that it moved down so fast. Now, whenever possible, I much prefer rotary motion. It's the easiest to design. You can use bearings to support the load. And if you go with a big radius, it can simulate a linear motion. So super simple design. A couple of bearings, the cylinder moves it. Make sure you run, before hooking up to the hydraulics, make sure you run it through and look for any binding points on the cylinders. Often we'll find that we will bind the clevis onto the other side of the mechanism. Now, another fun thing that is essentially a takeoff of rotary motion is 4 bars. And there's all sorts of different 4 bars that you can play with to do different things that can all be very fun. Simplest one, this is an equal length 4 bar. So it gets its name because you have 4 bars, 1, 2, 3, and 4. And this one's equal length. These 2 lengths are equal and these 2 lengths are equal. And so it provides, this output is always parallel to the input. And so like the gyrocopter on If Pigs Could Fly, and actually the rocket on Backyard Rocket, had this mechanism in there to move the gyrocopter and the rocket up and down. And then we added a pivot mechanism on top of it to tilt it. But so anytime you want something to move and stay parallel, this is a great option, especially for like a lift mechanisms. Now, if you go with an unequal length 4 bar, so all I did here is I changed the length a couple of these, and you can play with changing the lengths depending on what you want, but you can see we went from it being in a vertical here to at an angle over there. And so it's just, you'd hook up a cylinder somewhere on here to drive it up and down. And so it gives you a little different motion profile. Now, you can actually do what's called a reverse 4 bar. And so the output actually changes angle in the reverse way. And so it can give a neat thing. We use this on the head of the coyote on Cactus Practice, and it gave a nice motion. Another fun one is a linked 4-bar. So you have one 4-bar mechanism starting here, then you have a second one here, and so each one drives the next one. And so it starts to give you a curved output. So this can be very fun, other than you got to be careful about slop, especially if you're using this in a horizontal configuration. The other thing you need to be careful about is the speed of actuation. We use this on the tail for Just Imagine, and during our testing at one point, it was a horizontal tail, so it was sweeping side to side. At one point during our testing, we moved it so fast that the slop in it allowed the tail to come around and hit the side of the character. But that was we had 7 linked 4-bars in that one, so it was a little bit on the extreme side. Believe it or not, this is actually all 4-bar mechanisms being driven by a motor. So that's what the CAD predicted, but it's... And then this is the actual build. Now, luckily, that was after the parade was over, and we were running it. We cranked up the flow control on it as fast as we could go before the arm fell off. But that was just because there wasn't enough weld up here at the top of it. Now, this particular mechanism took a lot of time to engineer. However, I had the chance to talk to one of the judges after the parade at post-parade, and he said that this was one of the main reasons why we won a trophy that particular year. So it was a fun mechanism. Other options. So cranks. They are a great option for building mechanisms. It turns a rotary motion into linear motion, or oscillating rotary. One of the nice things is it basically gives you a sinusoidal profile for free. So if you watch the tip of this, as you get to the end of the motion, it slows down, speeds up, and then it slows down again and reverses direction. So it gives you a very nice, smooth motion without having to use the computer. The one drawback of something like this is you can't really sync the motions. So if you really want things to be looking in one direction, like if you use this for a head and you want all the heads to be looking in the same direction at the same time, a crank isn't a good option. But if you just want things to be moving and turning from side to side, it's a great option. So for if pigs could fly, this is what we put in for the pig heads. We didn't care which way they were looking. We just wanted them moving. And the other thing it allowed us to do was remove the pigs during decorations, because this was just a rotary motion, so we didn't have to rebleed the system. Another option you can do with a crank is a linear motion. Now, once again, you got to watch out that you're getting a high side force for a portion of it, and that could cause you problems in your design. Cams can also be fun. Truth is, I don't know that we've done any cams out at La Cañada. I know some other float builders have done them with very good success rates. So you start with a rotary motion, and then you just shape the cam to whatever you want. So here, you can imagine if this was a pop-up mechanism where you just wanted something to pop up out of the ground, you could do this. Burbank, I think it was, did one where they had 5 or 6 of these cams rotated at different angles along one shaft, and so it gave them a sequence for things popping up and down. but it gave a good way of doing a nice motion without relying on a computer to do the motion. This is one I actually did on an early float at Cal Poly, and it's a linear cam. So we use the computer to drive it forward and back to move a character or side to side on the float, but then we also wanted him to tilt as he got to the side of the float and wanted to control exactly where he was. And we didn't want to do it as two mechanisms because if he tilted too early, it'd cause a collision. And so by setting up the cam, it allowed him to move to the edge of the float and then look down at the right moment. And so it gave us a complicated motion without being a complicated mechanism. Sprocket drives. I love designing stuff with sprockets. There's so much stuff you can do with sprockets. It allows you to just link multiple rotary motions together. And it could be, things don't have to be the same speed. Changing the size of the sprockets allows you to change it. You can use idler pulleys, sprockets to reverse directions. But make sure you've got a way to tension the chain in there. And one of the hard things is getting all the sprockets coplanar as you initially set it up. If they aren't on the same plane, we've noticed that by the end of the parade, we can actually eat away the sides of the sprockets, that it just wears enough in the course of just the parade. Or the chains can actually come off the sprockets. And you can transmit motion a long distance with sprockets. Couple examples of different sprocket drives. So while this looks like a gear drive, these gears never actually touched each other. There was a sprocket system hidden behind it that was actually doing the driving of the mechanism. And because of the gears mesh in one direction, sprockets mesh in a different way, we had to use an idler to reverse the direction for this middle one so that they would all work together. Here's another one where we had 4 things that we wanted spinning at the same rate. Now, this happens to be the idler sprocket in this case. And the location of the idler sprocket is very intentional because when you're wrapping a sprocket or a chain around a sprocket, you want to make sure you have, I would say, at least 90 degrees of contact, 60 to 90 of contact, or else the sprocket may skip teeth on the chain. So by putting the idler pulley in this location, we were able to have a nice 90 here, better than a 90 there. We got a 90 there as we came down, and then another 90 and around. So here we've got those sprockets that are, or those gears that look like they're intermeshing, but they're actually being driven by chains on the inside. And that allowed us to have this run without having the wearing off the deco material on the outside of the gears. So if we talk about feedback for a minute, a lot of the floats use open loop control. So where you just tell it, I want to go from point A to point B, and it just goes. And it travels at a single speed back and forth. And nobody actually knows where anything is. Our computer allows us to use feedback. So the computer not only knows, there's the cylinder that makes it move, and then there's the feedback that tells it where the mechanism is at any given point. And so there's a whole feedback loop that is comparing where it's supposed to be to where it is, sending a signal, causes the cylinder to move, the sensor determines whether it's in the right spot, feeds it back in, and it keeps doing this loop over and over and over again, many times a second. Now for us, one of the things, so you've got to find a spot to put the feedback in. One of the things you want to do is you want to use as much of the stroke of the transducer as you possibly can, but make sure that you don't, that the transducer is never being used to stop a mechanism. So we have a lot of 9-inch transducers that we'll use with 8-inch stroke cylinders. Gives us a 1/2 inch of extra travel at either end, but we're still using a majority of the travel. Any of the travel that you don't use is just a resolution of where the mechanism is that you can't take advantage of. We like to mount them parallel to the cylinder. It's just gives the cleanest signal between the computer and the cylinder to minimize errors and make it as easy on the computer as we possibly can. When you mount them, you don't want to have any extra slop in them. Keep those joints as tight as possible. Any slop is then uncertainty that the computer is trying to control around that it doesn't know. Couple different ways of doing feedback. One of them is a string pot. We don't use a lot of string pots, although they can do a very nice job and work well. They're also cheaper than the transducers that we currently use. The one thing you got to be careful around them. They've got a very fine string in them. Welding around them is a bad idea. Even cocooning near them, the cocooning material can get onto that string and keep them from being able to go in and out. So you got to make sure you protect them while you're doing those operations. They're spring loaded. If you let them snap back, pull it out and then let it snap back in, it can break the string. It can do all sorts of bad things. You want to make sure when you pull out, it's straight. Here's another time where we've mounted them slightly off of being straight, and the little wire will wear on the thing and will actually cut a groove. Now, one thing to be careful about with us is our string pots, we typically come in and we modify them from the factories. Our transducer system is set up that the computer puts out an 18-volt signal to the transducers, but it wants a 0 to 10 volt signal back. Now the string pots are just basic a resistor, and so if you put an 18-volt signal in, it'll give you a 0 to 18-volt signal back. But what we've done is we've mounted a 10-volt voltage regulator inside most of our string pots, so that it reduces the voltage at the string pot from, instead of being 0 to 18 volts, it gives us the 0 to 10. Now, by putting the voltage regulator in there, or it reduces the error because you're not concerned about voltage loss on the trip to the transducers. But the bigger reason why we did that, it was just to keep them compatible with the tempersonic transducers that we use. So this is essentially what the tempersonics look like if they were new. However, we typically have ours covered in all sorts of plastic to try and get a few years more life out of them. I don't even know how old ours are. They were all around before I joined La Cañada 20 plus years ago. So they're getting up there in age. They are larger than the string pots, but because of the way we've covered them up, they're a little more robust. When you're designing, make sure you keep room for these guys. I'm going to mention this one. This is a crazy thing that we did at Cal Poly once. And it's an alternate way to do control, the feedback. And I'm just going to mention this as something to think about. So in here, we had this driving mechanism that we had its own feedback on that was moving this arm up and down. And then we had a track that we wanted to keep to move essentially with this mechanism. And so what we did was, instead of putting a feedback on this mechanism to drive it at the same time as this one, what we did was we put a string pod right here that worked as a level gauge on another mechanism. And so as this mechanism pivoted up and down, it forced the track to move forward and back with the goal of keeping this level. Now, once we reach, because what we wanted it to do was, once we reached we wanted the characters to move forward, and then only when they reach the end of the track would they lift up off the ground. So if the arm rotates up, it caused the track to move forward. So as this one goes up, it pulls this up, which causes this guy to try and rise a little bit. And so then the computer drove it forward. And so it gave us a way to link a couple of complex motions in a very simple way, instead of trying to program the two profiles to be exactly the same. So this channel of the computer, we just set up saying, hey, we want to keep this at 5 volts or at the 50% all the time. And when we reach the end of the travel, it was able to go up on its own because the computer couldn't drive it any farther. Another place where string pots are really good over the Tempersonics is for rotary mechanisms. You can just take it and wrap it around the mechanism, and then as it rotates, it pulls the string pod in and out. Now, typically you'll need some form of an extension cable on there and have some place to mount the string pot. But it works really good for mechanisms that rotate more than 90 degrees. We use this on the excavators for 321 dig, where they were rotating 420 degrees, where a normal transducer would never have been able to do that type of job. Of course, while you're designing it, think about how you're going to get the hoses into place. This is off those excavators that I was just mentioning. So we set up just a big spot for slack for the hoses. By the time we were done, there was a whole bunch of bungee cords holding these up in place, and allowed, so as it spun, it just tightened or loosened this curl. Now, one thing we didn't anticipate was, as it did that, it actually caused some motion on these hydraulic fittings, and at least one of these fittings came loose during the parade and started to leak hydraulic fluid. Now, we happened to be lucky that year that an operator was sitting right next to that mechanism and had a crescent wrench in his pocket. And so we were able to pause the show for a minute, tighten the fitting as it got loose, and get it back up and running within about 30 seconds. So it wasn't a big deal. But if this had been one of the other excavator, we wouldn't have been able to get to it. Now, what I'd love to get out of locking out of it, not sure about the price, but it would be something that if we could get donated would be great, are these hydraulic slip rings. And so what it does is it has a few ports on one side, a few ports on the other side, maybe some electrical connections through. And so it will spin, but it still makes the hydraulic connections and electrical connections for you. And so if you ever have a mechanism where you got a lot of rotation and you need to get hydraulic fluid across and electrical connections across, seriously look into getting some of these. It'd be great. The other thing are there's companies that make these little tracks that you can put all your hoses in, and then that'll ultimately make your cable management a lot simpler. This would be another thing that if we can find a way to get some of it donated would be great. Calculations. lots of calculations that can be done. As a reminder, this was originally set up as a presentation being given to a bunch of engineering students at Cal Poly, so they were a little more calculation driven. But these are still things that you need to think about. So this is a spreadsheet that I set up at one point for calculating the flow rate through all the different valves on the float. Our valves have the ability to flow around 8 gallons per minute. And so you want, as you're designing the mechanisms, you want to make sure you're not designing something that's going to need more flow than we have the ability to do. So here, 16 channels of animation it's set up to be able to do. You put in the number of cylinders, the bore size, so a 2-inch cylinder, 1-inch rod, it calculates what the ratio is. The stroke of the cylinder, how long is it? So this was 4 inches. I'm saying in the animation sequence, we're using all 4 inches of travel. That says we use 0.05 gallons to extend it, 0.04 gallons to retract, because the side with the rod has a little bit less volume, and how long we want it to take. And then that calculates out a gallons per minute for that mechanism. And you can see it's very low. Now, on the flip side, low is good in that we're not flowing a lot of fluid. Low is also bad in that our valves, you're asking the valve to be a lot more precise in its metering of the flow. If you're trying to use a lot of flow, then the valve gets to move a lot. If you're trying to use a little flow, then you've got to keep the valve has to be a lot more precise in its control, because it's just oscillating a little bit to keep it at the right locations. So if you want something that you want to move extremely smoothly, even though you might not need the force from a larger cylinder, you still might want to use a larger cylinder to give you better control of the mechanism. Now, one thing, if you look down here, you can see right here, this mechanism said it needed 10 GPMs for a flow. We have 2 high flow valves, which I forget exactly what their flow rate are, but I think they're closer to the 15 or 20 gallons per minute. And so for that particular channel, we realized we had to put the high flow valves in order to get the motion, the speed of motion that we wanted for that mechanism. All right, so I've also mentioned doing some stress calculations, but for stress calculations, you need some sort of input data on how much is the thing going to weigh. These are the rules of thumbs I always used. When I was doing a first cut, back of the envelope calculations, 5 pounds per square foot. So if you've got a character that's all covered in carnations, 100 square feet, it's going to weigh 500 pounds. Or it's going to weigh 200 pounds if you cover it in a seed. Now, we could get more. I never felt it was worth going any more granular than this for my calculations. I mean, some of the things are a lot lighter, some of them are heavier, but keep into mind, this also accounts for the weight of the structure and the shaping and the screening and the cocooning. Now, if you've taken into account the weight of the structure separately, you can cut your numbers down a little bit. Now, these numbers also assume that the float is wet. I know we've only had rain on the parade once in the length of time I've been involved in the parade. However, the number of times it's rained on the float, at some point after when we left the construction site till sometime when we returned to the construction time, I don't even know how many. It's amazing how many days it's rained just after the parade. You get through the parade and then you get to post-parade and it gets wet. So we need to make sure we design around wet floats, not just dry floats. And I mean, some of the things on the Great Houdini, when it rained, we had dehydrated carrots all over the float. Well, we had rehydrated carrots all over the ground when we were done with that parade, as it broke through of its glue. But some good numbers there to use. So when should you do some calculations? I'll admit I don't do actual calculations on all of my mechanisms. A lot of times I just like, that's big enough. And truth is, that's bit us a few times. There's been times that Randy's gone in and modified my mechanisms because I didn't have enough force to do the job, because I didn't take the time to do the calculations that I should have. So if you're in doubt, do a calculation. If it's a large mechanism that will be over people, probably should do some calculations. If it goes outside of the pod footprint, so where it's got the chance of dropping onto the general public, probably a good idea to do a little bit of analysis. If the failure of that particular mechanism will significantly detract from the float, probably a good idea. I mean, that little mouse I talked about on the Cal Poly float from years ago. That one little mechanism, which was a nothing mechanism, so nobody ever did any calculations, it failed, and it really hurt the look of the float. We should have done some more calculations, or we should have beefed it up a whole lot more. Again, this is was more for the Cal Poly group, but factors of safety. So typically when we design something, we'll take the load. Okay, so we've got a character. We think it's going to weigh 600 pounds. And then we'll look at the beam that we're putting in there and go, well, 600 pounds out at some distance will cause this amount of bending stress in the beam. We're good to go. At JPL, we design it, even though we know what our loads are going to be, and we've got all these great analysis tools and people dedicated just to doing analysis, we still put in additional factors of safety, so that if there's a mistake in our calculations, we've got a little extra margin in there to protect us. And there we use factors of what we call 1.4 on ultimate and 1.25 on yield. To engineering students, this makes a little bit more sense. And if you guys have more questions on this one, I can go into more of that later. However, if we're designing ground support equipment, we're up in 4.5 G. Well, we're up at higher factors of safety. You can see here we're saying certain things we have to go with factor safeties of 5 and 3. Design factor here for transportation, we say we'll see 4.5 G's of loading, and still have to have a 2 factor safety of 2. Now this 4.5 G's is more for landing on an aircraft, but often for floats, I'll use something in the neighborhood of a 2 G's for when you drive over box dots with a float. It can cause a lot of bouncing. So a little bit more. So they say if we're testing for JPL 1.25 and 1.4, untested 1.5 and 2. So just question, do we do analysis well enough to justify those low? More of just anything. OSHA requires factors of safety of 5 on anything that's being used for lifting. The takeaway of all this is something in a factor of safety of around 3 is probably good. So, just take whatever loads you're calculating and multiply by 3, and that should give you about the right size. For when I was doing all the FEA analysis on the float and looking at a lot of different cases, I was going in the range of 2. But that was with a lot of analysis. Weight normally isn't an issue, so beef it up when in doubt, and make sure you think about safety. Since I mentioned safety, just a few things to, like I said, more for the Cal Poly things, but all sorts of different ways people have gotten injured. So think about it as you're out at the float site. Make sure you're thinking about watching for safety issues, keep people from doing stupid things, and try and get we've been lucky that we haven't had any real major issues for years, but let's try and keep that going. A few random resources. For anybody who hasn't looked at McMaster-Carr is a wonderful resource for buying stuff. It is essentially, in a lot of ways, it was Amazon before Amazon's Amazon. It has a huge catalog of all sorts of mechanical parts, sprockets, gears, solenoids, cylinders, all sorts of different things that you could ever want. And delivery times typically in the day to 2 day times. And you can, if it's something important that you absolutely have to have, they have a distribution facility in Santa Fe Springs that you can actually drive and pick up the stuff. MSC is another good website that has a lot of good industrial type things. I believe Dwight picked up a bunch of these little fluid power data handbooks. I've actually keep mine at my desk. Don't buy them on Amazon. They're like $25 on Amazon. When I did this, they were $10 for 10. I think now they've gone up just a little bit, but very good resource. Other self-builts and people. Okay, let's talk about actuators and control systems for a little bit. There's lots of different ways to move things. So I already talked about different types of mechanisms, but this is more on the actuators used. Common actuators. For linear, we got hydraulic cylinders, pneumatic cylinders, and solenoids. Hydraulics are good for big, heavy motions. Anything where you want a lot of power, a lot of good control. It's our go-to. Pneumatic cylinders aren't very good for big stuff, but they're good for smaller stuff. And I'll get back into that in a little bit, as well as solenoids. As far as rotary, you've got hydraulic cylinders can be used for rotary, although those start to lose their effectiveness when you start pushing past 90 degrees, especially 120 degrees is really pushing the limits of how much rotary motion you can get out of a hydraulic cylinder. Electric motors can be good, hydraulic motors, and then there's things called rotary actuators, which I'll talk about in a couple minutes. Pneumatics. Okay, pneumatics we don't use much, but when we've used them a few times to great effect. They're fast acting. They're easy to install, no bleeding, no. Typically the hoses are just a little push to connect, quick fitting, so no even tools really required. They're good for small motions, but don't expect to stop them anywhere mid-throw. So they will extend, they'll retract, extend, retract. That's all you're going to get out of them. Limited force capability. Don't expect to move a big mechanism with a pneumatic cylinder. And you need some form of an air source. When we used them in the past, Dwight was kind enough to let us borrow his air compressor and put it on board the float as our air source. And it worked perfectly fine. So it's got a very simple system. I mean, especially when you use something like an air compressor, all you have to do is run a hose from there to the solenoid valve, and then a hose from the solenoid valve to the linear actuator. So this happens to be one you can see right here. This is a little valve that we own. And then you can see these little white lines are the lines to the actual cylinder. Because pneumatics are compressible, where hydraulics are essentially non-compressible, it's more important to keep your valves close to your mechanism. Just it'll reduce the amount of compressibility in the system and make it a little more fast-acting, rigid system. When we first put these on, we didn't use silencers on the output, because you can just, instead of having to route the air back to tank, you just let it go off into the air. But there's little things called silencers that reduces the noise as it comes out, because the psh, psh, psh outputs of the valves actually became noticeable over all the other noises of the float. So we ended up adding some silencers on there. I think the float that we use it to best was this one here. So watch the hammers right here on the xylophone.
I had to navigate horse coming around that corner.
Randy did a very good job of with the mechanism and programming it to get those things in sync with the music. And while I'll often say that a small mechanism like this isn't necessarily worth the effort, this is one of those times where a small mechanism was definitely worth the effort. It was right up in front, super visible on the float, and I am convinced that this particular mechanism here won us the banner over. I think we would have won it with the other stuff, but this one just put it over the top, because when the judges came up to this float, two of the judges immediately walked up to the xylophone and started just watching the xylophone and watching it play the music. A third one started to walk around. One of the two judges ran over to the other judge, pulled him back to the front of the float, and they watched this mechanism for a good minute out of their 5 minutes, just staring at this one thing and how it was synced with the music so well. And that's where the pneumatics really excel. And just because I've got this image up here, I'm going to point out the door to get into the driver's compartment was actually a lift-up door, and the seam line is right along here and right along here. And this is another one of those times where instead of trying to hide the seam line, we actually accentuated it by putting different colors. We put different deco materials on the two sides. And so now the shadow line, which was the door, actually just looked like a design detail instead of a door. So something to keep in mind. And also the visibility for the driver is actually right here, right underneath one of the xylophone keys, made for a great visibility. Another option, electric motors. These things are super simple. Most of the time we use them with a fixed speed, although you could vary the voltage in to get them. Most of them you need some sort of gearbox or a gear motor to get them going slow enough. A lot of these motors run at like 2,400 RPM or more. But like this little one, back when I did this presentation originally, it was $35 for this motor, and it turned at 50 RPM. And so we use these on a couple of different floats. We used them to drive the wheels on Dinosaur, but they were a little underpowered, and we burned up a few of them by the end of the parade. But they're good for small mechs. I just wish we had gone and bought a little bit bigger ones. They were originally bought for doing the lights on the top of the excavators, where they did that job very well. Hydraulic motors, another great way to do rotary motion. Watch out, there are a couple of different types of hydraulic motors. There's low speed, high torque, and high speed, low torque. For most of what we do, you want to make sure you're using the low speed, high torque motors. Otherwise, you just won't get enough power out of them to move the mechanisms. The nice thing here, a flow control valve, and you can change the speed. One thing to watch out for is the temperature of the hydraulic fluid varies quite a bit different between when we start the parade and the end of the parade, and it gets a lot easier to flow. And so your flow control valves may have to be adjusted during the parade in order to slow down the mechanisms. Or the other thing you can do, and what I like to do, is put in a gear reduction, just another little simple sprocket drive. And so it does a couple of nice advantages. One, we're now less susceptible to the change in speed. If we get a 10% change in the motor speed, but we have a 3-to-1 or a 4-to-1, we only get a 3 or 4% change in the speed of the motor. Now, they do make out there temperature compensated flow control valves, which we don't own any because they're a lot more money. But you wouldn't have to worry as much about changes in hydraulic temperature or if you had one of those. Like I said, hasn't been worth the money in the past. The other nice advantage here is these little motors often don't have the capability of supporting the weight of the mechanism. Now, if you've got something really lightweight and really simple and you just want it to be moving a little faster, yeah, just take a sprocket, drill a few holes and bolt something onto it, and you've got a spinning mechanism for super easy and almost no work. If you got something a little bit bigger, add the bearings to give a little bit of extra support to this structure. Rotary actuators, we don't have, as far as I know, we don't have any, but these things are very neat and something to consider depending on what your mechanism is. And what these do is you would control them with a hydraulic valve off the computer like any other cylinder, and you'd have to bleed them like any other cylinder. But instead of using a linear cylinder to then create a rotary motion, it just creates rotary motion. So you got a little vein right here, you put fluid on this side, it turns it one way. You want to go the other way, you put fluid in the other side, it goes around. It can be hooked up to a mechanism. Depending on the design of them, it can actually be the entire mechanism. And it's often smaller in size for doing the job. So this is one of those things that I would say, if we can get some donated, that'd be great. The other thing would be take a look at eBay and see if we can find some for cheap. Different types. This is a rack and pinion drive, so it's got essentially hydraulic cylinders that then drive a gear. This is a vane type. There's another company out there called HELAC. At least in the past, they weren't willing to donate to us, but they have, it is your bearings and your rotary actuator all in one thing. So it's essentially a complete mechanism ready to go. Some of them have extremely high load capacities. So depending on your float, if you really need something like that, these are out there. Solenoids. Solenoids have almost no force at all. They're even worse than pneumatics. But they're simple to control. They only require power getting applied to them, and then they move. They can be either normally open, normally closed, or normally extended, normally retracted. So another one of those things that you could think about using. We've used them once that I know of, and that was for this shell game here. And we went to the solenoids because there's actually a solenoid hidden in each one of the balls in order to actuate a gate latch to determine whether or not the ball is visible or not. So when the cup comes down, it triggers a gate latch that then pulls the ball up into the cup. When it comes back down, the electrical contact is made to the float, which then allows you to energize the solenoid to keep that ball in place during the sequence. Oh, just going to mention this one. It worked great in testing. The problem we had during the parade was that was the wet parade. All the roses swelled up during the parade, and they actually pushed the balls off of their mounts because we didn't set the roses quite low enough. So if you ever do something similar to like this again, make sure you really do a better job of compensating for the decorations than I did on this one. As far as controlling them, I've mentioned these a few times, but so we have a manual proportional valves, directional hydraulic valves, flow control valves, and proportional hydraulic valves. In today's, a lot of people think that digital is better. Well, in reality, digital just means that it's repeatable. So when you talk about a digital hydraulic valve, normally what they mean is a bang bang. It's on or off. And so you have no control of speed. We have these proportional hydraulic valves, which allow us to control the speed, which gives us our smooth animation and what gives us why this feedback works. But let's start with the basic manual valves. These things are simple, they're reliable. One of the neat things about them is since it's being manually done, the show is always different. There is no repetitiveness. However, you want to put your animator in a spot where they can see the mechanism. And something in the range of 4 channels is about the maximum that any given animator can control at the same time. We typically only use them for stow mechanisms, but they can be used to great value for an actual parade operated mechanism. A lot of the professionals don't go with computer controlled animation because of the cost of setting up the feedback, the computer, the programming time. It's just not worth the cost. And they can get people to come in and pay them $100 or $200 to ride on the float and animate the float during the parade using manual valves. One of the big advantages of them is depending on your sequence or your show, you can actually play to the audience or play to the cameras a little bit more, or because you can change the show for that period of the parade. Now, like I mentioned earlier, the biplane that Burbank had on their float was all manual animation, and they used a slightly different valve. They've got all sorts of different valves out there, but they used a 2-axis joystick which controlled side to side and up and down on one controller, and I think it even had a thumb control to control the spin of the plane. So everything was on the one control. Now, talking with Steve Edwards, who animated that, he said that at the end of the parade, his arm was just extremely sore from animating it the whole time. So something else to keep in mind. Directional valves, as I mentioned before, these are digital, no feedback required. They just move from point A to point B. So you say, I'm going to turn the valve on for 5 seconds, the cylinder is going to extend. I'm going to turn the valve on for the other direction for 5 seconds, it's going to retract. Typically, you'll put flow control valves in line with them in order to control the speed at which the mechanism is moving. This is one of those places where as the hydraulic fluid changes temperature, it's going to go faster and faster. A couple of different ways. One, just set all your flow control valves when your temperature of your oil is nice and hot. So you just have to make sure on the morning of parade, start your engine up early, get that hydraulic fluid temperature up to temperature so that so it's running at the right speeds as you go through cameras. No feedback. You can put limit switches in if you want so that you extend until you hit a limit switch, then you go back. Now, often you can spot mechanisms that are controlled this way on floats because it'll get to the end of the travel and the mechanism will jerk a little bit because it's traveling at full speed until it gets to that end of travel, and then it jerks, and then comes back, hits the other end of travel, jerks, and back and forth. Not exactly what we like to do, but they're simple. Proportional valves. So this is what we typically use. And so instead of the valves being forced into either the extremes, they will adjust to whatever position they need to in order to be as controlled by the computer. Can give you very repeatable motion. It is feedback is highly recommended. And oil temperature doesn't really matter because the valves and the computer are controlling for it. And if you've got a complicated sequence, this can be much better in that it is a repeatable sequence. So years ago, we did
Here's the winner of the Bob Hope Humor Award.
And so
that was renamed just recently, you know.
So this one goes against a bunch of my things. It's got dedicated Stow Mechanisms. It's got collision zones, but it worked.
Cactus practice.
Other than the one mechanism where the valve failed on us.
A trio of singing saguaro cacti.
But the mouths were actually all synced to the motion.
Built float. That means the volunteers from the city.
There's a reverse 4-bar inside of his neck.
Cool
Water. Written by Bob Nolan. Bob Nolan, Tim
But if you
Spencer,
want
Roy
to get
Rogers
something where you're really syncing to the animation, you've got to go with the proportional valves.
That old wily coyote fur is a combination of several different shades of cotton and pampas grass. His beard is really...
For controlling hydraulic motors, it's really simple. A little flow control valve, you can see them right across here. And then I highly recommend an individual ball valve. One year we tried just doing one master one. You can see how there's a master valve here to turn everything on and off. The problem we ran into was during deco week, they'd want us to move one mechanism. And so what we had to do was close all the other flow control valves and then open just the one flow control to move it a little bit. And so that caused some safety concerns because there was a chance of moving the wrong mechanism. And it also meant that we had to readjust all of these very late instead of being able to just use them adjusted from where it was. So having the individual ball valves is very useful. When you're working with cylinders, a few things to keep in mind. Design to the full travel of the cylinder. These cylinders, even a small cylinder, an 1.5-inch cylinder, can create over 2,000 pounds of force. And if you don't design to that whole thing, you can break stuff. So even don't ever count on the computer to say, oh, we're only going to travel 6 inches out of the 8 inches of throw. Something will go wrong. Something will happen. You will travel that full 8 inches and you will break something. So design to the full travel. If you can't, stop the travel of the cylinder down. Stopping it isn't the best option. It works. The problem with stopping it down is it makes it harder to bleed the cylinders and get all the air out. But if you have no other choice, you can do that. You can either put stops inside of the cylinder, or you can put them on the outside. External collars work really well. You can get these little collars in like 1/2 inch or 3/4 inch thicknesses for basically any cylinder rod size from McMaster car. We've got a bunch in the trailer. They just drop around and are a really good option when you design it to use the whole thing, and then shaping finds they can only use 7 of the 8 inches of travel. Go in there at the last minute, throw a couple of collars on, and call it good. Cylinders should only be used in tension and compression. They are not designed to support a bending load. Don't count on a cylinder. Don't just take a character and hang it off the end of a cylinder unless it is a big cylinder and an extremely light character, because what you're going to do is you're going to put a load on the sides, and you're going to wear out the seals in the cylinder, and it's going to cause that cylinder to start to leak. And of course, it won't start to leak until the worst possible time, being judging or as you're going through cameras. That's when they always leak. And make sure when you're mounting them, use cylinder, some sort of a clevis, and that they don't bind. Like I said earlier, they only have limited effectiveness over 90 degrees of travel, just because your lever arms for your cylinders start to drop down so small that you're not putting the force in the way it needs to go. And try to minimize your slop. Slop is something that if you use a 3/4 inch clevis pin for a 1 inch hole in a 1 inch hole, you've got a 1/4 inch of slop, and that's just so before the cylinder can do anything, it's going to move through that slop, and that's something that the computer can't control because it doesn't know about that. So how to keep your slop out? Tight clearances. For our 1 inch diameter cylinder or clevis pins, we have a 1 inch reamer. I know reaming stuff sounds strange, but it actually helps a lot. If possible, design your mechanism so that the center of gravity never goes over center. If it always keeps the cylinder loaded in the same direction, then even if you've got slop in the system, the slop isn't changing from one side to the other. If you can't do that, sometimes it's worth using 2 cylinders going in opposite directions so they're fighting each other, or adding a spring or a cylinder to add a force to artificially move the CG. As you're designing your animation sequences, do not stop the mechanism near the CG. It's just, it gives a, you can actually get into a feedback loop, and it causes some real problems there. Control systems can't hide all mechanical issues. Trying to design and build your things correctly to begin with. Here's an example of some counteracting cylinders. So one cylinder was used to go one direction, the other cylinder was used the other way. And so it always kept tension in the system. When you're calculating your cylinder force, you're putting fluid in one side and fluid comes out the other. If you're pulling with a cylinder, you've got less force than when you're pushing with the cylinder. And when while we run our system around 1500 PSI, I like to use 1000 PSI or even a little bit lower than that as my assumed pressure for all my mechanisms. One, you're going to lose a little bit of flow as you get closer and closer to the limit of the cylinder. Also, our system only has a top pressure around 1750 PSI. And so if you design around 1000 PSI and you need to bump up the pressure a little bit, you've got some overhead there to play with. If you start by designing around 1500 PSI in the system, you don't have much extra room for mistakes. Whenever possible in designing, I like to use bearings. We have a lot of these pillow blocks. Now, these need to be used in pairs. No more, no less. The thing is, they're self-aligning. So there's actually a spherical bearing around the outside and then roller bearings around the inside. And so it will actually align the shaft. So even if you don't get your shaft, your bearing mounts in the exact right spot, it aligns them together and gives a nice straight path. If you put 3 on, now they can't align, and one of them's in. If you don't get them perfect, then they're fighting each other. If you put 1 on, there's nothing that keeps them from just rotating any which way they want to go. They're easily available. Chuck has got a source to get these for cheaper than what you can get them from at McMaster Car. They're mainly good just for radial loads, although they can take some thrust loads. But if you've got a lot of thrust load, I'd look at adding additional something to take out the thrust load. There's also these little needle bearings. These are really nice. They can take some extremely high loads, and they're really cheap. I mean, they're a few dollars at McMaster Carr, but they do recommend that they use them with hardened shaft. So not just the cheapo shaft that we get from our steel supplier. It needs a hardened shaft so it doesn't damage them. They don't take any thrust load, but if you've just got something that's going up and down, they're small. It's nice to use them in pairs, but if you're using them in pairs, I would say start with a bigger piece of stock and drill a single hole so the holes are known to be concentric, and then push them both into that block. Don't try and mount them at a long distance as a pair, because we don't have the capability of making them the parts that accurate. If you need thrust load capability, they have these thrust bearings. They work really simply. You just a couple of hardened washers, and then the cage assembly and another hardened washer, and they take a thrust load. So, and they have take up almost no space, and they are cheap. So if you got like just a character sitting on top of a bearing that wants to spin from side to side, instead of using 2 plates with grease, putting something like this in will make the thing reduce the friction and will make it spin a lot nicer. Other things that you can sometimes use as bearings are spherical bearings. They typically have a little more stiction. They're not as easy to turn as something with actual roller bearings in them, but they're self-aligning. They can take some really high load capabilities, and they can be integrated into these rod ends that you can buy for relatively cheap. And so you can get some nice advantages on them. Here, this was a mechanism for doing butterfly wings. And the nice thing here is the actual bearing portion that had to stick out near the joint line for the butterfly is very small. And so we were able to use those rod ends as a bearing in that case. But we also use them here as part of our linkage. This is a crazy link mechanism that I can talk about later if people are interested. Another option, sometimes just go with a nesting tubes. It's cheap. It's small. So here, I've got one mechanism that tilts this shaft side to side. Then I also wanted it to spin. When I started looking at getting bearings that were big enough to do the load, it started getting too big. And I said, you know what? I'm just going to go with a greased design. So this is a 3-inch pipe with 3.5-inch tubing. 3-inch pipe and 3-inch tubing. So there's pipe sizes and there's tubing sizes. Pipe sizes aren't actually the size that they say they are. They're slightly bigger. And actually you can see I added some collars on, so we're only at a few spots instead of the entire length of there. And then we just filled it with grease. Another thing, we've got a couple of these. They're big turntable bearings. These will take thrust loads. They'll take moment loads. They've got a nice large opening in the center, so you can run things up through the center. If you have to buy them, they're extremely expensive. Last I heard, Burbank has a source to get these donated, but we also have 2 of them. You can also use the torque hubs as bearings if you want to. They're normally designed to be used in a horizontal configuration, and that's the way the oil will get to everything. If you're pointing them up or down, just make sure you put lots of oil in them to keep them lubricated. We use them as a gear reduction and not as a bearing as well. So, I mean, they're 20 or 40 to 1 speed reduction hubs. So sometimes you just want a lot of torque or slower speeds, and that can work there. There's a thing called reversing the splines. On the drive ones, there's a push button that allows you to engage or disengage the gears. So if you're just using it as bearings, you want to pull that, reverse the spline on the end. So it's basically take the gear out, spin it 180 degrees around and put it back in, and then all the gears aren't spinning and you get a lot less drag. Going to talk a little bit about judging. I don't know if this is still true, but at least at one point this was the scoring sheets. Just pointing out floral, roses, color are the ones with the big impacts. Animation, humor, not so much. 24 awards last I checked, or when I did this one. We all know that Bob Hope Humor Trophy is like our top award. But keep in mind that there are 2 reserved for floats under 35 feet long. Now, when the floats that are under 35 can get those 2 plus any of the other ones, floats that are over 55 feet and can't retract within 55 feet are only eligible for 3. So be very careful about breaking that 55-foot length number. But I'm going to mention you can never predict the judges. They're always different. Sometimes they like certain things. Sometimes they don't like things. Don't put too much weight on winning an award. Make sure you're just building the float that you want to build, and that it's, and I always feel that a crowd-pleasing float is more important than a winner. And I'm just going to mention a couple other things that actually Dwight's very familiar with it. Audio, you don't necessarily need a lot of power in your amplifier, but make sure your speakers have a good line of sight. That cocooning or foam really reduces the amount of energy that gets out of the float and bounces it back down into the operators. Light dusting of deco material can be all that's really needed, or hide it with a bush. Couple of spots where we hid speakers. So on Mechanical Melodies, we actually cross-shot our speakers. We put them sent them the sound energy the opposite way, so that the surface that was less visible to the judges in the crowd was the one that the sound energy was coming out of, and this side, the drum head, actually had a nice floral on it. Same float in the back. We just put a scrim and then put a bush in front of it. Here, we hid them, for Scissored Wizard, we hid them inside of these things. So we had a nice black surface, that just a light dusting of onion powder, and we shot the energy out through there. Watch out for your dynamic range. You don't want things that go from very softly to very loud, because nobody will ever hear the soft stuff. Get your music clearances. Builders have been sued in the past for not having the right clearances for both the rights usage and performance. So watch out for that one. Some royalty-free spots. And smoke can be used effectively at times, but be careful. It does behave differently during judging during the parade, because the float's not moving, and also humidity can have an effect on how much smoke you get. One nice thing is you can get a lot of smoke out of a smoke machine in a very small package, but as I said, environmental conditions can make a difference on that. And that is everything in that presentation.